so forth into general relativity. And it's actually a pretty simple observation, one that you'll probably all be like, shit, I could have guessed that, damn. Have you started it?
Yeah.
Okay, good. At any rate, so what I'm going to do is I'm going to start by a reorganization of an old principle. And I told you last time what the Einstein's observation was going to be based on. So I'm going to start with an old principle that will be eventually deepened. As we go. And this marker is already dying. All right. So, from considerations of Newtonian gravity and Newtonian mechanics, those are two separate subjects, remember. Newtonian mechanics is where you use F equals ma to solve problems with many different forces, and then Newtonian gravity is the specific expression for Newton's universal law of gravitation. But from considerations of those two aspects of old physics, we can arrive at what is often called the weak equivalence principle. Or the WEP. Okay? And it turns out that the weak equivalence principle is based on, really and truthfully, just realizing the equality of two distinctly defined things. Okay? That is, the equality of the gravitational mass of an object or a system of objects and their inertial mass. Okay? Now, obviously, the gravitational mass plays a fundamental role in the definition of the gravitational force. If we're near the surface of the Earth, we know that it just takes this value. But of course, we can appreciate that this is just the gravitational field. So we can sum over G, mg, I, r minus ri cubed times r minus ri. Okay? So again, this is the definition or the expression for a single type of force. Okay? And it's a gravitational force, and that's where the gravitational mass plays an important role. And then, of course, you also are aware of the role that the inertial mass plays in, for example, Newton's second law, where we take a system, we sum all of the net forces acting on it, and that is equal to the mass, the inertial mass times the acceleration. And what's important is that this incorporates all forces. Okay? So the inertial mass plays a role which is relevant for any force that's acting on an object. It doesn't have to be gravity. However, the gravitational mass only arises in its formal definition in one force. That's the gravitational force. Okay? Now, one force, and that's gravity. Okay? Now, we can take both of these and consider what we can do if there is only gravity in the game. Okay? Yes?
So are you saying that there's two types of masses, or?
I am saying that there are two, that the notion of mass appears in two fundamentally different contexts. There is the gravitational mass, which is a quantity which determines the strength of the gravitational field. And then there is the inertial mass, which is the resistance to acceleration given under the sum of all forces acting. Okay? So this could include the electromagnetic force, the weak nuclear force, all these forces. Okay?
Are you saying there's two properties of mass?
There are two different definitions of mass. We, of course, inertial mass is equal to the gravitational mass of every object. But they're not defined in the same sense. This is defined in terms of the gravitational force. This is defined in terms of the inertial properties. Okay? It's just two different ways of defining them, but they happen to have the same value. Okay? All right. If we have only gravity, then we, of course, discover that the acceleration of the system is equal to the gravitational field, because the mass here and the mass here cancel out. If you only have gravity in the problem, the only force on this side is the gravitational force. So this is mgg time equals MIA. You can cancel out the mg and the mi and you get A equals g. Okay? Which, of course, we can contrast with E and M, where with E and M we have that the acceleration of an object which is only experiencing an electromagnetic force, the acceleration ends up being Q over M times E. Because charge plays the role in the electromagnetic force that mass plays in the gravitational force. This is the mass that goes over here. It's the inertial mass. So if you say I only have an electromagnetic force, that's basically QE equals MA, so A is Q over ME. Obviously, the advantage that gravity has is that the mass goes here and here. This is, of course, G. Mass over mass is 1 because they're the same. Okay? Y'all following this? It's pretty complex shit, isn't it? I'm just kidding. Okay. So, what we are going to do is we are going to slightly modify this into what is often called the weak equivalence principle prime. Okay? And the weak equivalence principle prime is essentially that A equals G. Okay? So let me say this in words, and it just follows from what I just did here. Okay, obviously if the only force in the game is gravity, then A is equal to G, and that hangs critically on the equivalence of gravitational and inertial masses. Okay, so we can either take this as the starting point, or we can take this as the starting point. Okay, where I'll attach some words to that just to flesh out what I mean. So here we go. For massive objects and external gravity, and by external gravity I mean I'm taking an object and I'm considering the gravitational pull of an external object. I'm not talking about the gravitational self-interaction of a mass. Okay, so we have a ball, it's made of lots of little atoms, each of them have a mass and they're attracting each other. We're not including that as part of the story. This is just an external gravitational force. So external gravity, a uniform external gravitational field is indistinguishable from a uniform acceleration. Okay? So, I want to draw a picture, as promised. So first of all, the Earth is blue. And the Earth, we know, creates a gravitational field. And so we can imagine being inside of a lab on the surface of the Earth and doing an experiment where we know that one of the guiding principles is that there is the gravitational field pulling everything down towards the Earth. So this thing is sitting on the surface of the Earth. It's not falling or anything. So, maybe I should just draw the bottom of it touching the Earth. Okay. So for example, as an experiment, we might just do a simple projectile motion. So we take a ball and we throw it. And that's what it does. Okay? Now the weak equivalence principle, prime, basically says the following. If I take my lab and I put it in deep space, okay, so no more Earth, just deep space. And I take the lab and I give it an acceleration, in this case in the upward direction, which is coincidentally equal to minus g. Okay, the gravitational field has dimensions of acceleration, so obviously I can swap out a and g. So we're accelerating in the opposite direction from the gravitational force. But if we, in this instant, take a ball and throw it up, what will it do? Let me ask a person. Skylar. Skylar, what will the ball do if we throw it up in this situation? The same thing, exactly. You might think, oh, if I take a ball and I throw it up and I'm in deep space, it's just going to float in front of me. No, folks, this thing is accelerating upwards. So it's going to follow the same trajectory. Okay? Everybody on board with that? Nothing new here, folks. Nothing new. Now, oh man, I think I could do this. D-per thoughts. We ready? What we're going to do is we're going to extend the weak equivalence principle to what is often called the Einstein equivalence principle, the EEP. I'm being very careful with the board today, so I have to write as little as possible. Okay? The Einstein equivalence principle says the following. For any objects, I erase the word massive and I put any. For any objects and any force except internal gravitation, a uniform external gravitational field is indistinguishable from a uniform acceleration. Okay? I literally just changed massive to any and external gravitational force to any force except internal gravitation. Okay? Well, what does this give me? What new effect does this give me? Let me see if, Drew. Any idea what new effect this Einstein equivalence principle will give me that I did not have with the weak equivalence principle?
You can bend light with it.
Exactly. You can bend light with it. Okay? So let's see. So what I'm going to do in this case is I'm going to work it backwards. So I'm going to go into deep space first. Oh, I thought I heard somebody online doing something. Okay, I'm going to go into deep space first, and I'm going to accelerate my laboratory upwards. Okay? And then what I'm going to do is I'm going to take a photon gun, and I'm just going to shoot out little blips of light. Okay? Now this is in deep space. There's no gravity around. Well, what's going to happen to the bleeps of light that I aim directly at the wall right here? What are they going to do? Shaylee, are they going to hit that target if I aim straight at the target?
They're going to hit slightly above.
Well, the rim's accelerating upwards.
Oh, so slightly down.
Yeah, so the light is actually going to go like this. Can anybody argue with that? I mean, you're moving the target. You're accelerating the target upwards. So if I aim straight at it and shoot, it takes time for the photon to go from the end of the gun to the wall, and in that time, the target has accelerated upwards. Okay? Does everybody buy this? You sure? Okay. Well, here we go. Let's Einstein equivalence principle it. In which case, if we're in a lab that's on Earth, and we take a photon gun, then the same thing must happen. Now I know what you're all thinking. I don't see any damn light then. Right? Yeah, it's pretty reasonable. Well, the thing to remember is, this is not a huge lab. In fact, we're going to find they have to be small. But at an acceleration A, which happens to be equal to minus g, the light going from the gun, cannon, whatever the hell you want to call it, the light goes from here to here so quickly that the acceleration really doesn't produce any effect. Okay? Of course, if we could measure with infinite accuracy, we would see the light deflected, or if we did this in a really big laboratory, we could see the light be deflected. Okay? But that's explaining why on Earth, usually when you shine a light beam, it seems to go straight, even though gravity is pulling it down. Okay? Okay, which one of these is weird? The one on the right. Okay? This is a new ingredient to the story, but we have to accept it. Okay? Now I will say, and I'll come back to this in a little bit, that these equivalences hang on the notion of small labs. And I'll talk about why that is in a few minutes. But now, well, there's only one thing we can do. We can go deeper. I know. You're like, what the hell? Shoot. Okay. We can actually take the Einstein equivalence principle and we can strengthen it into what is called the strong equivalence principle. And the strong equivalence principle says, for any object and any force, a uniform external gravitational field is indistinguishable from a uniform acceleration. We can include internal gravitation. Okay? Now, it turns out that the Einstein equivalence principle is all we need to develop general relativity. You might wonder, what does the strong equivalence principle do? And it turns out that if you start with the Einstein equivalence principle and you derive the consequences of that as your starting point, you can actually reach a couple of different results. Okay? So for example, there's something called the Dickey theory, which is another variation of general relativity. It's a little bit different than Einstein's finalized general relativity, okay? So if you just accept the Einstein equivalence principle, you could derive several different variations. However, if you accept the strong equivalence principle, Einstein's general relativity is the only thing you'll get. You won't get these other options. Okay? Now we won't really harp on that. We'll just take the Einstein equivalence principle. But now it is time. So are there any questions about these pictures and these equivalence principles before we move on? I mean, we're going to stay with equivalence principles, but just want to know. Yes?
It might be out of the scope, as you just said, but how does changing, allowing internal gravitation really affect it that violently? That only one theory, which is general relativity, is allowed versus the other ones?
So there's, I mean, I know one technical detail is that if we take the strong equivalence principle, we'll end up having to mandate a torsion-free connection. And you can not accept the strong equivalence principle and therefore not be forced into a torsion-free connection. Therefore, you'll have a more variable final theory. Does that answer your question? It's in the details.
I think to a degree.
It's in the details.
All right.
And we're going to go through the details in the formulation of general relativity. Yes?
The curve of the light we're seeing in those pictures, are those from a reference frame in the lab or outside of the lab? Or does it matter?
This is from the, oh, that's a really good question. So, that's a really good question.
Repeat the question.
The question is these curves that we see, is this based on what the person in the lab is seeing or what an external observer is seeing? Well, when you say an external observer, what do you mean?
A different inertial frame.
This is not an inertial frame. This guy's accelerating upwards. He's not inertial. An inertial observer, if they watch the guy shoot the laser, they would see the laser go straight. Because that's what all inertial observers see. This guy sees the laser bend down because he's in an accelerated reference frame.
Okay, so I guess something like, if say it was a ball and I was in that frame, if I were to throw the ball across, because I'm moving up and throwing the ball, that means I'm giving it an upwards velocity at the same time, so wouldn't it still appear to go straight? Like if you're sitting in a moving car tossing something, you don't see it move.
If you're sitting in a car tossing something, then you're tossing it in the direction of motion.
Or even
So I have in mind that I'm going to shoot this perfectly horizontal, orthogonal to the acceleration. Okay? And it's going to traverse at the speed with which I shot it in the horizontal direction. So it'll get from here to here based on the horizontal component velocity initial. However, because the room is moving up and it's accelerating up, and that's so important.
Sorry, okay. Yeah.
It's going to pick up a downward component to its motion,
Okay.
even if it starts out with none.
I think I was thinking at the constant.
Yeah.
velocity.
No, it's not a constant velocity. A constant velocity observer will see the light move in a straight line. That's an important observation. Okay? All right? Okay. So, the deeper thought. All right? In both Newtonian mechanics and special relativity, the concept of inertial frames play crucial roles. Okay? Hopefully you can remember what incredibly crucial role inertial frames play in Newtonian mechanics. Any takers? Actually, I'll just pick Sam.
Can you repeat the question?
What role does inertial frames play in good old Newtonian mechanics?
It gives you a baseline for which to measure things.
It does. Well, actually, you can measure in a non-inertial frame. You can get data from an experiment done in a non-inertial reference frame. But what can't you apply to the data if it's taken in a non-inertial reference frame?
Newtonian mechanics.
Newton's second law, basically. Okay? So if you want to use Newton's second law, you need your data to be the data associated with a inertial observer, okay? In special relativity, we formulate the framework based on the tenet that physics, including the velocity of light, c, is unchanged when viewed from different inertial frames, okay? So special relativity is a framework where we're saying there's an invariance, okay, of all of the equations of motion as long as they're written in a particular, starting with a particular coordinate system which is rectangular, and then using any coordinate transformation which preserves the metric, okay? So inertial frames play a very important role in both Newtonian mechanics and in special relativity. But what we might ask is, how do we find them? I mean, how do we determine whether we have an inertial frame or not? And the answer to this should roll off the tongue of absolutely any student who is studying for their Physics 1 exam next Thursday. So you should all know. How do you figure out whether you're in an inertial frame?
Newton's first law.
It's Newton's first law. Do you want to tell me what Newton's first law is and how we use it? You're right, that's the right answer.
Objects in motion stay in motion. Objects at rest stay at rest. If that applies, then
That's close. Anybody want to help her out?
Unless acted on by an external force. That last part? Or things moving like to stay what they're doing?
Maybe you guys should go study for the Physics 1 exam.
Well, you know what? I'm not
No,
studying
no.
for that exam.
I'm kidding. So Newton's first law, which in Physics 1 we often call N1L. Notice, this is the deepest part of the story, is Newton's first law. Okay, Newton's first law says, in an inertial frame, okay, then we bust into what sounds like a special case of the second law. That is, an object experiencing no net force will move with a constant velocity. Okay. So as it goes when I teach Physics 1, I say, well, this sounds a hell of a lot like a special case of Newton's second law, right? If the sum of the forces is ma, if the net force is 0, a is 0. If the acceleration is 0, that means the velocity is constant. So this sounds like a special case of Newton's second law. However, the most important words in this are right there. These tell you, they define for you, in fact, an inertial frame. All right? Now, aside from trying to balance forces so that there's no net force, and then if the object is moving with a constant velocity, we know we're in an inertial frame, we can actually step back and say, actually, I want a particle that feels no force. Okay, so here's what we could do. We can say, go to deep space, and we can set up basically capacitor plates. All right. And then if we put in a charge, say with the positive version of the electron charge, then we know what this object is going to do. It's going to accelerate to the right. However, if we put in a neutral object, that is something with charge 0, then the acceleration in this case is 0, all right? And so what we can use is this particle, this one here, and our observations of this to determine whether we're in an inertial frame. if we look at this particle, and this particle is moving with a constant velocity, it doesn't have to be at rest, because I could just boost myself to be moving with respect to it. But at any rate, as long as this particle moves with a constant velocity, to what I see, then that means that I am in an inertial frame. And notice there's no gravity because we're in deep space. Okay? If this particle is moving with a constant velocity, I am definitely not an inertial observer because I'm accelerating with the particle. Does that make sense? You sure that makes sense? Good. Here's the question. What do we do about gravity? What particle does not feel gravity? Massless ones? Nope. Does the charge matter? Nope. Everything feels gravity. So there is no way to look at an object which you know is not feeling the gravitational force and say, oh, it's moving at a constant velocity with respect to me, therefore I'm an inertial observer. Can't do it. What you can do is you can take an object into deep space where there's no gravity, and you can say, okay, now if I see it moving with a constant velocity, then I'm an inertial observer. But you can't do it when there's gravity present, because everything responds to gravity. It is the only force that impacts everything. And moreover, it's the only force that has the exact same impact on everything. A equals G. Remember, the electromagnetic force, A is Q over M times E. You can have different effects based on what the mass and what the charge is. For different particles, you get different accelerations. For gravity, it's the same damn acceleration for every single particle. It's G. Okay? So it turns out that figuring out how in the hell to define an inertial frame when gravity is in the game, and you've accepted Einstein's equivalence principle, it's really hard. It's really hard. And this is where Einstein made his breakthrough. What we want to do is we want to disregard gravity as a force. Now, we don't want to do this with other forces, but we want to just try and find a way to remove gravity from the equation. Because it's this annoying, constant, persistent thing that bothers everything. So, how can I, in the presence of gravity, near the surface of the Earth, how can I remove it?
Take away the normal force?
Unfortunately, no.
You curve the space so that comes up.
Nope. No, it's okay. These are good guesses.
I was going to say accelerate in the opposite direction.
Well, I'll put it a different way. You jump off a cliff. Free fall. Let's think about it for a moment. If I'm near the surface of the Earth, and I've got my lab set up with my capacitor. Okay? And of course, this is going to generate the E field in this direction. If I put in my Q equals E plus, and I put in my Q equals 0, what is the acceleration of the E plus going to be? To the right and down. It's going to have the acceleration due to the electromagnetic force, but it's also going to have the gravitational pull, so the path is going to be something like this. Okay? What about q equals 0? What's its acceleration going to be? It's going to be straight down. Oops. Not at an angle, straight down. Okay? Well, what I'm going to do is I'm going to FFF this. Once you figure that out, let me know. No one?
Flournoy free falling?
And I'm free! Let me remind you of what was giving us this headache. G. So, let me set up my experiment. Creating an electric field to the right. I'm going to put in a charge. And another charge, q equals 0. What was I supposed to do to get rid of gravity?
Free fall.
Jump off a cliff, go into free fall. So in addition to the presence of gravity, my lab is undergoing a downward acceleration, which has the same magnitude as the gravitational field. That's what a free fall is. This is a freely falling frame. And now I ask, what path is the charged particle going to take in this frame? It's going to go directly to the right. What path is the neutral particle going to take? It's going to sit at rest. We're talking about to an observer in this thing.
It's going to be a very short experiment.
That's actually a really important observation, which I'm going to harp on in just a moment. Okay? Now, that's cool and all, but check this out. Those are both equal. If you would like to experience life in deep space, jump off a cliff. Yes?
Does gravity still count?
Don't worry about that. We'll come to that. Okay, so I'm just talking about falling with your acceleration lined up with the gravitational acceleration, everything. Okay? Now, I want to reiterate that what really makes this work is the idea that the acceleration is equal to the gravitational field if gravity is the only thing in the story. This is for everything. It doesn't matter if you're a quark, an electron, a cow, or an elephant. It doesn't care. So if you think about the other three forces, electromagnetism, it only impacts charged objects. Strong interactions only impacts quarks. The weak interactions, they're kind of weird. But gravity is extremely universal. It not only affects everything, but it affects everything identically. So trying to beat gravity into a form that is taken by the other forces in nature, it kind of seems silly. It's way better to try and formulate gravity in terms of something universal that doesn't care what it is that it's impacting. Now, what we're eventually going to find is that there is one feature in physics which impacts everything. It doesn't matter whether you're charged or not, whether you're massive or not. And that's the geometry of space-time. So it turns out that by associating gravity with the geometry of space-time, this is going to fall out of it very nicely. Okay? Now, there's one big, fat caveat. How big are the labs? They're small. Why are they small?
Compared to the speed of light they are.
Compared to the speed of light they were, that's true, but why are they small for this to work?
Because their gravitational pull on the Earth has to basically be irrelevant compared to the gravitational of the Earth, or like the, I guess in comparison to the size of the gravitational object that's pulling on them. If you put another Earth next to it, it wouldn't really work.
Well, that's true, but
gravity's gonna pull on it like this if it's too
right, look. This is an acceleration in one direction. Every point in the slab is accelerating downwards. However, we know that gravity is not uniform. It points towards the center of the Earth. So technically, the gravitational fields point like this, different in different areas. This one actually is not accurate. Okay? So trying to replace, in this situation, this coalescing gravitational field with a uniform acceleration where everything accelerates together, that will not work unless your laboratory is really, really tiny. So tiny, in fact, that you cannot measure the different directions of the gravitational field. Okay? Now, I know many of you are going to be like, well, you know, we'll do an experiment in a lab of finite size, da 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 da. Here's the thing. This observation, that we need both a tiny, tiny lab and, what else?
Bigger.
Tiny, tiny lab and
Small time frame?
a small time frame. That's the definition of a tiny lab. It's small in volume, but it's also, whatever you're doing is over a short time span. You can use a long time span and see the effects. Okay? So, what this is going to lead us to is a restriction on the geometries that we're going to work with. Yes?
When you say small time frame, do you mean from like an external observer or from the internal?
Well, I'm literally talking about, let's build a building. How long do you want the walls? I mean, we'll all agree whether we're inside of it or outside of it. I mean, yeah, if it's moving really fast, there'll be a dilation of links and all that crap, but I'm just saying, we're going to do an experiment that's non-relativistic. It's not going to be moving quick, okay? So we don't have to worry about that. So I'm just talking about the physical dimensions and then the amount of time. Now the reason why this is important is because this is going to lead us into the allowed space-times in general relativity, and those space-times are called manifolds. And we are going to dive headfirst into manifolds next time, okay? But for now, the requirement that the lab be small such that everything works is going to be an important caveat, a big fat caveat.
How small are you talking? Are you talking less than 1, or are you talking about it must happen within the
Well, no. If you're, we'll talk about this when we actually define manifolds, okay? But when you're talking about experiments, then you just talk about your experimental accuracy. Then you just compare what you're measuring over a length scale to how much experimental accuracy you have. If you give a kid a ruler, you could probably use a mile-long laboratory. They'd never know anything. However, if you're using a spectrometer, you probably got to have a pretty small lab in order to produce results that are going to be consistent with a uniform acceleration up to the sensitivity of a spectrometer. So there's the experimental results, okay? And then there's the definition of this. And the definition of this I'll get to. But essentially, it's going to be based on the notion of a neighborhood of points around a point. And that neighborhood mathematically can be infinitesimally small, but it's still not zero. And what's interesting, and I'll just throw this to you, near the surface of the Earth, your lab can be pretty big and you won't notice anything. Put it near the singularity of a black hole. I guarantee you your lab will notice it. So, but we'll cover that in due time. Okay? So let me quickly write up on the board the consequence. Experiments performed in a small, freely falling lab over a short time give results that are indistinguishable to those in an inertial frame in empty space. Okay? This is the Einstein equivalence principle. Go for it.
Does the ISS count as a small free floating lab?
I would think so. Yeah, I would think so. Okay. So this is yet another statement of the Einstein equivalence principle, but that's what we're going to base this class on. Now, what I'm going to do now is I'm going to kind of give you a preview of where we're going to go. And then unfortunately next time, it's going to get pretty technical. It's going to get pretty mind-blowingly mathematical, but that's okay. I'm just going to show you the definitions, make you do a few homework problems, and then we'll carry on. But here we go. Let's compare special relativity to general relativity. So for special relativity, we could define it in the following sense. The laws of physics are invariant under transformations connecting inertial frames and space-time is isotropic in space and homogeneous in space-time. That is, the symmetry group is the Poincare group in 4 dimensions, which, as I mentioned before, is ISO 1,3 up, semi-direct producted with 4 translations. Okay? So special relativity is basically a statement about the symmetries. As long as you're in an inertial frame, you can do any transformation which is an element of this group, which will take you to another inertial frame, and whatever physics you're doing will look identical in that other inertial frame. If you want to go to an accelerated non-inertial frame, that's going to make physics look different. Okay? What's special is the transition between inertial frames. Okay? In GR, we're going to have the following. The laws of physics are invariant under. Now bear in mind, one of the ways of determining that you're going from an inertial frame to another inertial frame is that the metric remains the same. And that's how we derived this set of transformations. In general relativity, we won't have that luxury. So it turns out that in general relativity, the transformations you can do are wildly bigger than this set. In fact, in general relativity, the theory is invariant under diffeomorphisms of space-time, which we'll give a precise definition to next time. Okay? Now, so far what I've written seems a lot like special relativity. It's just the symmetry group is bigger, right? I mean, we'll define diffeomorphisms later, but this is a bigger set than this. So it seems like general relativity is just a more symmetric theory. But there's one ingredient to the story which radically changes the outcome. There's an and. And this and plays no role whatsoever in special relativity. And the connection for gauge field facilitating this invariance should be given, or sorry, it should be rendered dynamical by the introduction of an invariant field strength term. Now there's a lot of words after and that you don't know, and that's fine. We're going to define them all. Okay? So I'm not even going to try and hammer out what is a connection. Okay. But a connection is very much like a gauge field, and you might or might not know gauge fields. If you took particle physics, you sure as hell better know gauge fields. But if you at least took electromagnetism, you should have an idea of what a gauge field is. But I'm just going to summarize this. Everything after the and is saying we should allow the geometry to be dynamical. We could fix the geometry of space-time and explore the symmetries associated with it. But it's the and part that's saying, no, you can't just fix space-time. You've got to let space-time figure itself out by what masses and energies you put into it. And so to facilitate that part of the story, we have to add in a gauge invariant field strength term. And again, don't worry if you don't know what these words mean. But just to give you an idea, when you do electromagnetism, you could do electromagnetism in fixed backgrounds of E and B. Okay? Where you just say, I'm sticking a particle in that E field, what's it going to do? I'm sticking a particle in a B field, what's it going to do? Okay? And you can talk about what's going to happen in a fixed electric and magnetic field for different particles or with different motions or whatever. Or you can be honest and you can say, well, I have to generate these with the presence of charges. So these are actually solutions to equations, Maxwell's equations. Okay? And so in reality, I've got a dynamical background and particles responding to it. Letting these be dynamical through Maxwell's equations is exactly the second half of the story in general relativity. It's letting the background geometry be dynamical. And again, we're going to see how in due time. Now, we are going to start by doing the first part. That is, we are going to investigate the invariance of the laws of physics under diffeomorphisms. This is going to play out very similar to what we did here. Because after all, what this story brought us to were tensors. We said whatever is physical should be invariant under these transformations. And it turns out as long as it's a tensor, it's going to be invariant. But we had to figure out how to identify tensors, so we worked through how they transform. And then if you have a tensor expression, you can look at it and go, yep, that exactly transforms as a tensor should, therefore this is a physical thing. This is in terms of tensors. Well, in the GR story, we're changing the transformations. It's a bigger set than this. We are still going to have to define things which are invariant. And what do you think we'll call them?
Manifolds?
Say it again?
Manifolds?
No, these are physical objects. Manifolds is going to be relevant to the geometry. We're going to call them tensors, exactly. They're still going to be tensors, okay? It's just that their transformation properties are going to be somewhat different, okay? Now what's beautiful about this is that we're going to develop the transformation properties of tensors in curved space. Okay, this is this diffeomorphism. But you can always take it and simplify it back to this story. Okay, so we'll do that in numerous instances. Now, so I want to kind of give you an idea of what these are. And just so you recall, remember that in special relativity, if we did one of these transformations, then what we would do is we would take the x and t axis and we might, or actually we may take the x and y axis and we might boost it to a y prime x prime axis, which is moving with some velocity with respect to the original axis. Or we might just rotate it. These are universal transformations. If we're going to take this coordinate system and boost it with a velocity relative to the original coordinate system, we do that for all points in space, right? Or if we're going to rotate the coordinate system, we do that for all points in space. So these are what are called universal or global coordinate transformations. They apply to special relativity. Okay? In general relativity, we can do everything that you do in special relativity as long as we limit ourselves to a small lab that's in free fall. Because inside of a small lab that's in free fall, there's no gravitational effects. So physics should be described by special relativity, right? You agree? So I can take whatever I'm observing and I can boost, and then the boosted observer should experience the same physics. But unfortunately, it's only in this tiny volume. And for this volume over here, things can be different. So what we're going to find is that in general relativity, because of the curvature of space-time, where you can only eliminate gravity in a very small neighborhood, you are going to consider not global coordinate transformations, but rather local ones, where you do a little bit of a transformation here, and you do a little bit different transformation here, and a little bit different transformation here, and a little bit different transformation here. Now let me ask you, how many of you remember my lecture on groups? Remember when I talked about global versus local symmetries? Okay, if we took the translation, the global translation, everything looks the same, but the local translation, where you do different translations, it doesn't look the same. But if you take circles and you rotate them, global and local both give you the same thing. Okay? So what we're going to be starting with, this is just starting, is creating a theory which is invariant under these local transformations, and those are what are technically called the diffeomorphisms. Okay? These are often called general coordinate transformations. And again, since we're going to work with tensors, technically everything is invariant under these. However, most of our expressions will be written in terms of tensor components. So the tensor components will transform, but as long as you have the same kind of tensor on the left and the same kind of tensor as the tensor on the right of an equal sign, they'll both transform in the same way, so the expression technically doesn't change. We call that general covariance. I'm throwing some words out that you might or might not have heard of, but I just want to get you familiar with them, and we'll dive into all of this in great detail, okay? Now, let me very quickly, not that quickly, but just quickly enough. Well, actually, no, I've already said this. This is actually notes from a, so the last time I did this, I actually gave a quiz on this day. And so I took 15 minutes out of the lecture material, but anyway, this is a review. But, so I guess, yeah, actually we might end a few minutes early. But I do want to throw some nomenclature at you, just so that when you see this, you don't get confused. First of all, if you're ever given the metric as the identity, then this is called Euclidean space. In rectangular coordinates. Okay? If you're given the metric as -1, 1, 1, 1, this is, of course, what we called Minkowski space. In T, X, Y, Z. And these are, of course, special cases of geometries. If we go to more general geometries, then we have Romanian geometries, wherein the metric takes the form A, B, C. Okay, it doesn't to be diagonal, doesn't have to be a bunch of ones, with all of the elements being greater than 0. This gives me what is called a Euclidean space. Or sorry, this doesn't give me a Euclidean space. It gives me what is called a Euclidean signature space. That is, if all of the diagonal elements of the metric are positive, then it's called Euclidean signature. However, if the upper leftmost element is negative with respect to the rest of them, then we have what's called a Lorentzian signature space. Now I say that because as we approach curved spaces, the metric can be all messed up. There's no reason why it has to be a bunch of zeros and ones. But if all of the diagonal elements are positive, it is a Euclidean signature space. That is, it is a purely spatial space. Versus if that first upper left term is negative compared to all the others, then we have space-time, and that has Lorentzian signature. Okay? We're going to use examples of both throughout the course. You can apply Einstein's theory to both of these. And Euclidean signature spaces are useful because you can draw them. These are really hard to draw. Okay? So, once again, to apply Einstein's equivalence principle required a small lab and a short time interval. But what's cool is if you go into a very tiny lab and over a short time interval, this thing is in free fall, then everything that you observe is consistent with flat space that's being out in deep space, even if this is happening near the surface of the Earth. Okay? Once again, this is going to lead us to the notion of manifolds. And giving these a technical definition is where we're going to now turn next time. All right? That's it for today.
Quick question.
Yeah.
In the Euclidean space, is that supposed to be a 3x3 matrix, or is that?
It doesn't matter. I mean, you can have a 10-dimensional space, and as long as all of the diagonal elements are positive, it's Euclidean
So
signature.
is it still just x, y, z? Is that like I'm looking at the first one?
Oh, sorry. Yeah, no, you're right. You're right.
Okay. Okay.
Yeah,
Thank you.
sorry about that. That's a good observation.